All right, let's get right into it. If you're getting ready for placements, you know there's one topic that's pretty much guaranteed to pop up in every single coding interview: sorting algorithms. So today, we're going to go on a little journey, starting with the absolute basics and moving all the way up to the genius level stuff that powers the biggest tech companies in the world. Seriously, this is what separates a good coder from a great one. Okay, let's do this.
But let's be real for a second. It's a totally fair question, right? I mean, in Python, you've got dot sort. In Java, you have arrays dot sort. The tools are already built for you. So why on earth do interviewers from Google to Amazon to Microsoft want to watch you write one from scratch on a whiteboard? Well, it's not about memorizing code. It's about something way, way bigger.
And there it is. That's the answer. Efficiency isn't just some academic concept. Efficiency is money. Every single time you scroll your feed or like a photo or search for something, it triggers a computation on a server somewhere. Now, imagine an inefficient algorithm scaled up across a billion users. It doesn't just cost a little bit more, it can cost millions, even crores, in extra server fees. They're testing you on this to see if you get it, to see if you can think at that massive scale. So let's start where pretty much everyone begins. Imagine I give you a totally jumbled list of numbers and just say, sorted. What's the first, most instinctive thing you'd probably do? You'd likely just start looking at the numbers next to each other and swapping them if they're in the wrong order, right? Well, that very first thought you had, that's actually a famous algorithm. It's called bubble sort. A good way to picture it is trying to arrange your friends for a photo, sorted by height. You'd probably look at the first two people, and if the shorter one is behind the taller one, you'd tell them to swap. Then you'd move to the next pair and the next, and so on. It's super simple, it makes perfect sense, and you know what? It works, assuming you have a whole lot of time on your hands. The whole process is this kind of slow, methodical shuffle. And the very first run through the list, the single largest number slowly, and I mean slowly, bubbles its way to its final correct spot at the very end. But then you have to do the entire process all over again for the second largest number, and then again for the third largest. You can almost feel the processor groaning just thinking about all that work. And this right here is the villain of our story. Its time complexity is O of n squared. Now, forget the fancy name for a moment. What this really means is that the time it takes to sort grows exponentially with the size of the list. So if you double the number of items, the work doesn't double, it quadruples. If you have a list with, say, 1 million items, just forget about it. Your program would be running for days. This is exactly why you will never, ever find bubble sort being used in a real-world, large-scale application. Okay, so if that simple, brute force way of doing things is a total dead end, we need a much smarter strategy. And this is the moment where computer science gets really, really clever. Instead of trying to wrestle with this whole massive, jumbled list all at once, what if we just didn't? What if we just broke it into smaller pieces? This whole philosophy is called divide and conquer. And trust me, it's an absolute game changer. Think about how you study for your final exams. You don't just pick up a 1,000-page textbook and start reading from page 1, right? No way. You divide it by chapters, you conquer each chapter one at a time, and then you combine all that knowledge for the final exam. That is exactly what the best sorting algorithms do. And now we are entering the big leagues. Let's get to our first champion of divide and conquer, an algorithm that has a pretty great name: quicksort. The entire magic trick behind quicksort comes down to one simple but really powerful idea: the pivot. All you do is pick any single element from the array. It could be the first one, the last one, a random one, it doesn't really matter. And you basically make it the boss for this round of sorting. So here's the game plan. Once you've chosen your pivot, your only job is to rearrange the entire list around it. Everything that's smaller than the pivot gets moved to its left, and everything that's bigger gets moved to its right. And boom, just like that, your one huge problem has now become two smaller, more manageable problems. Then you just do the exact same pivot and partition thing on those smaller lists. It's this beautiful, recursive process that just cleans up the mess incredibly fast. So here's the thing you have to remember about quicksort. On average, it is an absolute speed demon. It's incredibly fast. But it has an Achilles heel. If you get really, really unlucky with the pivots you choose, like let's say the list is already sorted and you keep picking the smallest element as the pivot, it can totally choke. Its performance can collapse all the way back down to that O of n squared nightmare we saw with bubble sort. Now, it's rare, but that risk is always there. Now, if quicksort is like the flashy, high-risk, high-reward race car, let's meet its counterpart, merge sort.
You can think of this one as the dependable, unstoppable tank that never has a bad day. It is all about guaranteed performance.
So merge sort takes that divide idea to its absolute extreme. It just keeps splitting the list in half over and over and over again until it's left with nothing but a bunch of tiny little lists that have only one element each. And what's special about a list with just one item? Well, it's already sorted, by definition. The real genius happens in the second step, the merge. It intelligently and carefully combines these tiny sorted lists back together, pair by pair, making sure that each newly created list is perfectly ordered at every single step of the way.
And this right here is its superpower. With merge sort, there are no what-ifs. There is no worst-case scenario where it suddenly grinds to a halt. It guarantees that top-tier, super efficient O of n log n performance every single time, no matter what the data looks like. And that rock-solid consistency is absolutely priceless in the real world.
All right, it's time for the face-off. We've got our simple beginner, and we've got our two advanced champions. Let's put their stats side by side and see the final verdict.
This little scorecard pretty much tells you everything you need to know. You can see bubble sort is just stuck in the slow lane, with O of n squared across the board. Quick sort is blazing fast on average, but it's got that one risky worst case that drops down to O of n squared. And then there's merge sort, the consistent champion, always delivering that O of n log n speed. The core ideas say it all. We went from simple swapping to these really smart strategies of dividing and conquering.
But these big O notations can still feel a bit abstract, so let's make it super real. Imagine you have a list with just 10,000 numbers that you need to sort. The difference is absolutely insane. To sort those 10,000 items, bubble sort would take roughly 100 million operations to finish the job. Now look at quick sort and merge sort. They take around 133,000. That's not just a small improvement, it's a completely different universe of efficiency. This is why these big tech companies care so much about this stuff. It's the difference between an app that feels instant and one that feels broken. And all of this brings us to the final, really critical question, the one you're actually going to face. You're in that interview, you've got the whiteboard marker in your hand, and the pressure is on. You know that quicksort and merge sort are way better, but they're also much trickier to code perfectly from memory. Bubble sort is slow as anything, but you could probably write it in your sleep. So what do? Do you go for the simple code that you're guaranteed to get right, or do you risk implementing the complex, high-performance one? See, that's not really a computer science question. That's a strategy question.